Okay, let's do a quick review of where we were last lecture. Last lecture we were talking about the fact that most analog circuits today end up driving basically digital systems. And so at some point in our system we need to quantize our signals, right? So we sample them in time and also sample them in space, and so we get a quantization effect. And we can characterize that quantization effect with basically, if we assume that the quantization is uniform, then you can show that the SNR, the effective SNR of a quantization signal, goes like 1.76 plus 6.02 times the number of bits. So if you plug in like 8 bits in there, you get about 50 dB of SNR. So it's very useful to do the opposite. If you have an amplifier that has a certain SNR, it's very convenient to express what the effective number of bits are in that amplifier. Okay, so I think we also talked about this slide as well. So one of the issues with analog circuits, just to review very quickly, is that if we want to increase the performance, if we want to, in other words, increase the number of bits, in other words, increase the SNR, we have to increase the capacitance. And because the bandwidth of the circuit comes out to something like GM over the capacitance, in order to keep the same bandwidth, we have to increase the GM. So to get one extra bit out of an analog circuit, we need to increase the capacitance by 4x, because the SNR is determined by KT over C. That means increasing the GM by 4x. Now, if you want to increase, keep your V star constant, in other words, if you want to keep your headroom the same, that means you have to increase your current by 4x. And so ultimately, analog circuits do not scale well as you keep the headroom constant, as you keep the supply voltage constant, and try to improve the performance, or even keep the performance constant. You have to pay a big price in power dissipation. So in this particular example, if you have a 15-bit ADC and it's consuming 100 milliwatts, if you want to add just one more bit to that design, without doing any calculations, without running any simulations, you should expect the power to go up by at least 4x. Okay? And that's just the reality. If you keep in the same process and want the same SNR, right, you're going to have to pay a 4x penalty in power. Okay. So in some ways, one take-home message from this slide is that over-design is very expensive. So if you're the type of person who says, well, let's be conservative, let me put in an extra bit in my design. Well, maybe 2 bits, so that I get it back and it meets specs. Well, that 2 bits is going to cost you a lot of power, right? It's going to cost you 16x in power, and you'll probably lose your job. So not a good idea. So you can't be too conservative in your designs. You have to actually have a good design procedure that can get you circuits that are close to the fabricated results. I'm not sure where we stopped exactly last lecture, so if I'm going too fast, just slow me down. But again, this is just another slide that illustrates this point, that if you want to calculate the dynamic range of an analog circuit, you could say that for the most part your signal swing is determined by your supply, right? There's an overdrive factor that comes in there, right? But the first order, it's VDD over 2 if you're not using any inductors. The noise, as we've seen, goes something like KT over C, noise variance power. So noise voltage, total voltage noise, goes like square root of KT over C. And because we're using active circuits, there's an extra factor in there, right? And we're calling that NF. Don't confuse that with the noise figure, by the way. It's just a notation that tells you the additional noise that's being added by the amplifier. And last lecture we did a simple calculation of NF. So dynamic range is just the maximum signal over the minimum signal. That's the signal range over which your analog circuit can process, right? If signal's bigger than that, you're going to clip. If it's smaller than that, your signal's lost in the noise. So that tells you roughly what the range of signals that your circuit can handle. So if you take that ratio, you see that the dynamic range is proportional to VDD, proportional to square root of C, and the rest of the things are more or less constant. So with a given supply voltage, the only way to improve the dynamic range is to improve the capacitance. Okay? Questions or comments? Yes?
Just going back to the last slide, how is the bandwidth like exactly related to the SNR, like GM over C bandwidth?
Well, to first order, it's not related, right? I mean, what we want is we have to meet a certain bandwidth specification depending on the signal we're processing, right? So someone says you have to process a gigahertz of bandwidth. There's nothing you can do about that, right? So in our traditional way of thinking of SNR, it has nothing to do with bandwidth, but in reality, of course, it does, because the bandwidth also tells you how much signal processing capability you have. So if you can come up with figures of merit to your heart's content. You might say, well, it should be SNR times bandwidth, right? That's a better figure of merit. Okay. All right. So here's an example which kind of brings everything home. Let's say you have a modern CMOS process with actually this is now an old-fashioned CMOS process by today's standards, but let's say you're using a thick oxide device and you have 3 volts of VDD. And on chip, what's the biggest capacitor you can integrate? Well, 1 nanofarad is pretty big. If it's a linear capacitor, that's going to take a lot of chip area, but okay, just for argument's sake, let's say you've managed to integrate 1 nanofarad capacitor. Of course, driving that capacitor is going to require a lot of power. But okay, let's not talk about that for a moment. Well, with these numbers, if you just plug into that last equation on the bottom here, assume NF is 1, basically optimistically, you get a dynamic range of about 18 bits, 110 dB. Okay? That's more or less the best you could possibly hope to do, right, in this process. There's no way you can claim that you're going to design. So if you're at ISSCC and someone says, I have a circuit and it's a 1 volt process and I get 150 dB of dynamic range, you're going to say, what? How do they do that, right? So you really have to re-examine and see what the magic is. Because if there's no magic, it's not going to work, right? Let's compare that to what life must have been like for our grandparents, right? Our grandparents had it a lot better. They had 30 volt op amps, right? They had plus and minus supplies, right? So they probably had negative 30 as well. And they're on board, so they can put pretty much any value of capacitance they wanted. But let's just use a number of like 100 nanofarads. Plug it in, you've got 23 bits of dynamic range. So definitely going on chip is not all better, right? Everything does not improve. You actually pay a big price for going to a lower supply voltage. And as many of you know, this is in contrast to digital circuits, where lower supply voltages and smaller capacitors are actually a good thing, right? Smaller capacitors mean less CV squared power. Lower voltages means less V squared in that CV squared. So definitely scaling in some ways is bad for high dynamic range analog circuits. All right, questions or comments? Philosophical comments? Anybody want to contest that? Okay, so we are falling a little bit behind, so I want to quickly go through an example here without going into all the gory details, because I think it's simple enough that most of you can do this as a homework assignment. But what we'd like to do is calculate the noise performance of a cascode amplifier. And the reason that we want to do this one pretty carefully is cascode is definitely the building block for analog circuits. It's one of those, fantastic configurations that just by chance it gives you everything without penalizing you too much, right? So why is a cascode so good? First of all, let's just review some 140 material. What are 3 benefits of a cascode, let's say? Okay. How about somebody who hasn't spoken up in this class before? Remember, 5% of your grade is participation. Okay. Turns out now I have all your pictures, so I can call on you. Anybody want to volunteer?
Peak output resistance?
Because of output resistance? What does that give us? So what's the advantage?
By GMR?
Yeah, exactly. It gives us really good gain. So a cascode amplifier is really a 2-stage amplifier, right? So what we're doing is we're using a current buffer which lets us go into a domain where we have very high impedance, as Toda is pointing out to us. So we have very high impedance at this point, so we know that we have a very large voltage gain because RO is large, right? What are some other advantages of this circuit? Tim?
It's unilateral.
Yeah, it's more or less unilateral, and if you took 142, you know what that means. It means that the output and input are very well decoupled. If in a single common source amplifier you have this feedback capacitance, so the output and input are coupled. Here they're very well decoupled. What's the advantage of having it unilateral for analog circuits? Yes?
There's no implicit feedback.
Yeah, there's no bandwidth penalty, right? We know that in a common source amplifier we've got C mu, Miller effect, and so if we have a large voltage gain, we pay the price with bandwidth if we're driving with any input source resistance. Here, because this buffer stage keeps the internal voltage gain low, there's very little feedback, and so this is actually a very broadband amplifier. So it's got gain, it's got bandwidth, and what's a third advantage? Yes?
It has good power supply rejection.
Okay, and that's again because of the unilateral properties. Let's look at something simpler. If you have a... Go ahead.
The noise of the cascode doesn't show up at the output.
Very good, and this one is not obvious, so we'll talk about this in more detail. So the noise performance is almost as good as just having M1 alone, and that's definitely not obvious unless you've done the calculation. Let me just point out one more thing, and that's power consumption. This is a two-stage amplifier that shares the same current, so it naturally has current reuse. People publish papers where they say this is a two-stage amplifier where I have current reuse. Well, this thing naturally does that, right? The DC current of M2 and M1 is equal, and so it's actually pretty nice. You don't have to dissipate more current to actually get two-stage amplification. What's a disadvantage of a cascode?
Output swing?
Yeah, so let's say the minus is lower swing, and that's definitely something to consider as we go into deeply scaled technology, because as it turns out, not only do you have the swing limitation of this cascode, but of course to get the high gain you're going to have to make this current source also a cascode, so then you're really going to suffer from voltage gain, and we're going to talk a lot more about that in today's lecture. Okay? Alright, so let's go back to the slides. In the slides you have a pretty detailed analysis of basically the transfer characteristics from all the noise sources to the output. Again, I'll let you guys go through this in detail and we'll just point out the pertinent results. If you look at this expression, you've got basically the drain noise of the second device, the cascode device. You've got the thermal noise of the first device and the second device here. And basically, assuming these are the dominant noise sources, we'd like to calculate the noise transfer characteristics. So here's the result. The result is that the output voltage noise has basically a component that looks like this. This is the noise sources, so it's first noise source plus the second noise source multiplied by some gain factor which is frequency dependent. So the gain factor goes something like omega over omega p times some second order transfer characteristic that basically is the bandwidth of the overall circuit. Now what's really pertinent here is omega p. What's the frequency of omega p? Because if omega p is low enough frequency, the second device M2 will contribute significant noise. Well, after doing the algebra, you find that omega p is just Gm over C. Gm2 of this transistor and C, which is the total capacitance at this node, Cx. Okay? Now, we're not going to intentionally put capacitor there, right? That capacitance actually represents the parasitic capacitance at that node. So it's the drain to bulk capacitance, the source to bulk capacitance. gate to drain capacitance of M1, and most importantly CGS of M2, right? Now if just for argument's sake, how big is omega p roughly? What's an upper bound on omega p? Anybody want to take a guess?
Omega t, because it can't go further than omega t. That's GM over CGS.
That's right. So the upper bound would be omega t, unity gaining frequency, because Cx is basically a bunch of parasitics. It's CGS of 2 plus C gate to drain of 1 plus C drain to bulk of 1 plus C source to bulk of 1 plus C wire plus everything else, right? But hopefully if this term dominates, then we have GM over CGS, which is basically the omega t of the device, right? If we include C gate to drain, then that takes one more term in that expression. Well, the good news is that omega t is a very high frequency, right? In a modern process, it might be 70 gigahertz. And that means that this noise term, IN2, is not significant. This term becomes equal to this term when you get to the frequency omega p. Let's say at the end of the day that when I design this amplifier, omega p works out to 10 gigahertz, okay, for the current levels that I bias it in. Well, that's great. That means that you have to get to 10 gigahertz to really see the noise of the cascode device, right? So here's a nicer, cleaner expression that really shows that. If you look at the total noise that you get from the device, it has a contribution that just looks like the noise of M1, right? This expression, forget the F, looks like just the noise of M1. And then you have this gain factor, which is the noise of M2. And you can see that it's also proportional to the ratio of GM2 to GM1. If these devices are equally sized and they conduct the same current, the GMs are equal, and the argument we made on previous slide applies. So what really hurts us is parasitic loading at this node. And so we're going to use every trick in our book to minimize that parasitic loading. Now, what tricks are we going to use to do that? Yes.
Multi-finger.
And what else? In particular, what are we going to do with the multi-finger device?
You don't need a drain contact there.
Yeah, exactly. That's what I was looking. You're going to share the junctions of that device, right? So you're going to actually, let me draw a picture. So instead of having two transistors like this and actually connecting them with a piece of wire, that would give us wire capacitance, and you'd get two junction capacitors. I can just share. I can actually just share. I don't need to contact this point. My contacts are out here. So over here, these are the contacts to connect to the metal. Here I don't put contacts, and that means that this actually is even smaller than this. Because if I put in a contact, I actually have to make this. This design rules tell me I have to surround it with some extra space. So here, since I don't have a contact, this can be very small. And so the capacitance from this node to ground is minimized. And this is just for a single finger device. I can design a multi-finger version of this if the devices are the same size. So I have gate 1, gate 2, gate 1, gate 2, and I share multiple junctions to even further reduce the capacitance. Okay? Questions about that? Okay, just very quickly, since I didn't do the algebra on the noise, I wanted to just show you guys who haven't seen this before why the cascode device does not contribute noise. And we're going to do a very simple calculation. So you can do all the algebra, but you won't get much intuition unless you play with the results, as we've seen in these slides. And then once you play with the results and you see that that cascode is not contributing much noise, you can do a simple calculation like this to find out what's going on. So let's call this I drain 2. This is the noise due to the first cascode, due to the cascode device. Let me just represent the output of the first device with an impedance Z1. This is CGS of 2. So this is the equivalent circuit for my cascode. And in particular, I'm concerned with this noise. Now the noise of this first transistor, it just goes right to the output. It sees a low impedance because of this cascode, and this is a current buffer, so for all practical purposes, all the noise of M1 makes it to the output. Okay? So it's as if the cascode device were not even there. What's of concern is the noise of the cascode device. And you might guess that actually the noise of the cascode device is not going to make it to the output. It's just going to circulate inside this second transistor. That's what we'd like to show. Okay? So this is a simplified equivalent circuit. And what I'd like to do is calculate the noise, the total output noise. Okay? So the observation is that total output noise actually flows into this impedance. Let's call it Z equivalent. Z equivalent is 1 over j omega C output plus 1 over RO of the device plus 1 over j omega CGS 2 of that device. And that means that the VGS of the transistor is minus I/O times Z equivalent. Right? So just this current flowing into this impedance produces a VGS across here. So if I calculate now I/O, I/O has two components. It has drain noise of 2 plus GM VGS, but GM VGS is minus GM I/O Z equivalent. And so if I bring this over to this side, I have I/O 1 plus GM Z equivalent is equal to I drain 2. In other words, the output noise due to the cascode transistor is suppressed by 1 plus GM Z equivalent squared. So this is the intuitive result, that the action of the reason the cascode noise is not contributing is because it's getting rejected by this factor. And clearly we want this to be large to reject the noise. Right? That makes sense to everybody? And so what is that factor? So at low frequencies, Z equivalent is approximately the RO of the transistor, right? And 1 plus GMRO, yeah, that's a large number. So at low frequencies, definitely the noise is rejected. At really high frequencies, it's basically a bunch of parallel capacitors, and the biggest one is going to dominate. So probably CGS is going to be the dominant capacitor at high frequencies, right? The impedance of this node is going to be dominated by CGS2, and so if I plug in CGS2 into the expression, I have 1 plus GM omega CGS2, this is approximate at high frequency, squared. And if, of course, we now identify the denominator as 1 over omega t over omega, squared. And this is approximately omega over omega t squared I drain noise of 2. Okay? And there you have it. This is the exact expression that we had in the slides, which told us that the drain noise at high frequencies starts to matter with a ratio omega over omega t. Okay? Or in reality, this is slightly lower than omega t. But the important point is that it's really at high frequencies that this noise starts to kick up. Okay? Questions? All right, so here's a design example that kind of brings all these concepts home. Let's say you're designing an amplifier for a 16-bit ADC, okay? And you need 100 megahertz of bandwidth, okay? And you want to basically have a voltage gain of -1. So very simple, okay? So first of all, let's look at the design choices. So let's say we use a 0.35 micron device. Using a larger channel length has higher output impedance, so we might be able to more easily get gain. Turns out this example was actually done when 0.135 was the class example. Here I should have redone this in 0.18, but that's okay. These are just some simple assumptions about the amplifier. Just to keep things simple, we're going to make M1 and M2 the same size. We're going to do a cascode amplifier. It's probably not the best choice, but it does keep things simple. And so in this equation, there's this factor F, which is the ratio of CF to the sum of all these capacitances, CF plus CS plus CP, making the assumption that they're all equal gives us F of 1/3. Okay? And so then we plug in. So dynamic range of the circuit is, of course, the voltage swing. Let's assume that it's Vs over 2. Kt over C times this factor F times 1 plus this extra noise factor. And if you actually solve these equations, basically you're just using the assumption that, so I should have stated where this assumption of omega u comes from. So we're assuming that we're going to sample the circuit at 100 megahertz. Okay? How fast does the circuit actually need to be? Well, we're actually going to make a closed loop amplifier. This is not going to be an open loop amplifier. So when we do a closed loop amplifier, it's going to have a settling characteristic, which is a function of the unity gain of the amplifier, right? Since the gain is -1, the settling time will be exactly the unity gain of the amplifier, closed loop amplifier. Actually, the open loop amplifier, because the loop gain is 1. Well, because there's a settling time issue, so the idea is that I'm going to have an amplifier with some feedback in it, and what I'm going to do is the input is changing continuously. I'm going to only run this circuit in discrete time. So at one discrete instant, I'm going to charge up this capacitor and then transfer that charge here and produce an output voltage. We're going to talk a lot more about these circuits later, but the idea is that because of the settling time of this circuit, it's going to look something like this, the output voltage. And we have to wait for it to settle long enough so that we get close to the actual true value before we say that we're done with the sampling process, right? So if I stop right here, there's going to be a huge error just due to settling time. If I wait too long, basically I've wasted my time, because actually the quantization noise that I'm going to get from my A to D converter is going to be much larger than this settling time error that I would get because I've basically didn't wait long enough. So there's pretty much the best point to stop. So I should stop at a point where the settling time error is less than the quantization noise. Okay? And we're going to do this more careful calculation later, but for the purpose of this example, you can actually see it very simply that the number of time constants that you should wait is related to the number of bits of accuracy you want. Because the settling time is a exponential process, It's the inverse of that, so you get a log relationship. So because I want to settle with to within 16-bit accuracy, that tells me how many time constants I need to go. All right. So this is where this number, this is where the omega u of the amplifier comes from, and that's of course directly related to the GM and the total load capacitance I have to drive. And let's assume that V star is constant, let's say a couple hundred millivolts or whatever the case may be. And so we solve these equations, and again, this will be a good homework problem for you guys. You've done something similar to this already without considering noise. And here's the result. And so again, our specifications were 14 bits, 100 megahertz, 1 volt swing, 200 millivolt overdrive voltage. This is we have to drive, basically to get this resolution, 14 bits, we need 26 picofarads of capacitance. This is our GM in order to get the settling time. This is our total power consumption, and this is our device size. And remember, the devices are equal. Quickly redo that calculation to get an extra 2 bits, and you see a huge difference, right? You'll notice that you have to pay more than 16x in current to get that extra 2 bits, and that jives well with the calculation we did earlier where we found out that every bit costs us 4x in power. Okay? And also it costs us a lot in area too. I have to make my transistors larger, I have to make my load capacitance larger, and so making going to higher resolutions has a power penalty and an area penalty. Okay? Questions or comments about this example? Yes.
So in example, the V star is fixed 20 millivolts or so. How does the choice of V star change over process over scaling?
Yeah, it changes in kind of a subtle way. Kind of a rough rule of thumb is that you should operate your transistor with a V star roughly n times Vt. Vt being Kt over Q, n being subthreshold swing, right? So probably, you know, if your subthreshold swing is 2, right, then at 50 millivolts overdrive, you're at more or less the border of operating in weak inversion. So to operate in strong inversion, you want to be, let's say, a factor of 2 away from that, at least 100 millivolts. And if you want to be in moderate inversion, you're going to be somewhere in between. The choice changes a lot because as the transistors get faster, you don't really take the speed penalty when you operate closer to, let's say, n times Kt over Q. Okay. Any other questions? Okay, so we're going to switch gears now and talk about a new topic, current sources. And basically a lot of this is review, so we can go fairly fast. When we talk about current sources, these are the kind of design objectives we have, right? Let's take an example. I'm going to use a current source as an active load, right? So what do I care about? I care about its output resistance, because that's going to determine how much gain I get in my circuit. What else do I care about? You could just say it. You don't have to use the mic. Swing, I heard. Very faintly, but I heard it. So swing. Basically, how far can I push this current source before it starts? So if I look at the characteristics of this current source, it has something like, does something like this. Very high impedance, and then it goes into a low impedance state. So this is kind of Vmin, the minimum voltage I can apply across this current source and still keep it alive. Okay? What else?
Variation over temperature.
Good. So basically, let's just say precision. So I don't want this current, maybe I do want it to change in a given way, but let's just say for now I don't want it to vary with process. In other words, let's say I want 50 microamps. if there's process variation and I get 60, 75, 20, right, I'm going to be in trouble. I want this to be very well controlled current, very precise current. So I want to have low systematic error. So basically I want this to be 50 microamps very accurately, and I don't want it to vary with process and perhaps with temperature. Although in a lot of circuits we actually do like it to vary with temperature so that it can compensate for gain variations. Okay. What else would I like? What have we been talking about past couple lectures, right? Noise, right? So we want good noise performance because clearly this current source is going to add noise to this amplifier. In fact, you guys did this for your homework. You looked at a PMOS current source and you figured out how much noise it added to the overall circuit. And you found there's a direct trade-off between the noise of the PMOS device and the swing, right? You have to make the V star large to get low noise, but that directly eats into your swing. Okay? All right. So that's about right. That's the things that we care about. And so the simplest current source that we know and we love is the current mirror, right? Simple current mirror. So the current mirror, don't have to explain how it works to you guys, but what we're interested in is what's the noise, because this is something that we haven't looked at before. First of all, let's just very quickly review some of the characteristics. So what's the Vmin of a current mirror? What's the lowest voltage I can take it? Well, it's so simple that there's no calculation required. I just have to keep this device in saturation, right? For a long channel transistor, that means that the output voltage has to be bigger than the overdrive, right? VGS minus VT. Or for our device, let's say some factor K times V star. Okay? Because in a modern transistor, the transition between saturation and triode is not so clear, right? And so really what we want is to actually go in and measure the output resistance of this device and say, well, I know that if I'm, let's say, 1.5 times V star, the output resistance is high enough, right? So in practice, we usually determine this experimentally, you know, using SPICE, but to keep this discussion simple today, we can just say V bigger than an overdrive voltage. Okay? What else? So how accurate is it? Well, we're going to talk about matching later. Basically, I have a bias current here. Let's talk about systematic error. What's the systematic error between the output current I out and IB? Anybody? If these were bipolar transistors, what would the systematic error be? That's right, base current. It would be due to base current. Well, how about for MOSFETs? That's right. You want to use a mic?
Difference of the VDS of the two transistors.
Very right. That's exactly right. So this device is operating at a constant VDS equal to VGS. This device, though, has a VDS that can vary all over the place. And because it has finite output resistance, its current is going to vary. So there is a systematic error which is on the order of 1 plus, let's say, VDS minus VGS over the early voltage. Okay? That's pretty much it. Of course, you know, if we don't lay out these devices correctly, there's going to be other kinds of systematic error. Definitely you want to lay out these devices close together with the same layout, right? You don't want to, you know, even though in theory only the W over L ratio is important, you better use the same L, right? And so then that means use the same W for both transistors. Well, the nice thing about this current mirror is that you don't actually have to have the same W over L, right? I can have a current gain, which is W over L2 divided by W over L1. Okay? So this current gain could be 5 or 10. It's nice. That means that I can have one reference path running at low current, and I can gain that up for my actual amplifier, right? I don't want to waste current in my bias circuitry. Well, we'll re-examine that assumption. But the important point is that if I'm going to scale W over L's, I definitely want to do it with copied devices. So the dumb way to do it would be this. Right? This is my minimum size transistor. This is my wide transistor. I connect my gates together. And this one is a diode connected device, right? This would be really stupid. Why is that?
Yeah, the devices don't really match. I mean,
Yeah, this is basically going to have a systematic matching problem because this tiny device is very sensitive to lithography around it, right? So the edge effects, and it's so small, the effective W is going to vary. Whereas this device, it's wide, and so it's not going to have, only the edges will get affected by lithography. And so you might think you're getting an integer ratio of, let's say, 5, but you're going to end up getting something different. So there's going to be a systematic error to start off with. And the way to solve that, of course, is very similar to what we talked about in the first couple lectures, is we realize this device with actual discrete devices. And we can interdigitate the device, so this might be this device here, and these would be the output devices. Okay? And this, and then you could put them on a quad to try to minimize gradients and play all the same tricks we did with our resistors. Of course, the limitation of this is that it requires an integer ratio. Usually that's not a problem, right? You can live with an integer. As it turns out, so this is just a systematic error. There's also a huge benefit in doing this for random errors, and that's related to the gradients and things like that we talked about earlier. Okay, noise. Let's calculate the output noise of this device. Okay, it's a very simple calculation. It's basically the drain noise of this transistor plus m squared times the drain noise of this transistor, where m is that current gain ratio. Okay? And so I just plug in, well, the drain noise is proportional to gamma times gm. You guys know this very well now from previous lectures. And so I can write the total noise in a really nice way. I can write it as 4kT gamma gm times 1 plus m delta f. In other words, the noise looks like it's coming from an equivalent resistance Rn. Right? So the noise is basically 4kT 1 over Rn delta f, where Rn is 1 over gamma gm 1 plus m. Okay. Now this is really interesting because it tells us that this Rn is definitely not related to the output resistance of the device, right? I can actually write this in another form. I could say that GMRO is the voltage gain, the intrinsic voltage gain of the device. So I can write this as RO over AV, and then this extra factor. And because RO is the actual resistance of the device, the noise resistance of the cascode is actually, the current mirror is actually a voltage gain times smaller, right? And this might be 10 or 20 or whatever, or 100 for a long channel device. Is that good or is that bad? Any comments? Yes.
it's bad, right?
Yeah, it's terrible because this current source, it's good because it gives us high output impedance. It's bad because it's giving us a lot of noise, right? The smaller that resistance, the more current noise we get. So, unfortunately, using a current mirror means that it's very noisy, and it's going to add substantial amount of noise. So if you could use a physical resistor with resistance RO, you'd be much better off, right? Because it would contribute very little noise, 10 or 20 times less noise. But why is it that I don't use a resistor? Okay, I think everybody knows the answer, so someone just say it. Get your 5%. Can you use a mic?
You'd have to use a really large resistor.
Okay, but let's say that my uncle is in the resistor business, so I have access to big resistors. What's another reason I wouldn't use it?
It's noisy.
No, we just showed that it's not noisy. I think you're asleep. No, actually a big resistor is good, right? It would contribute very little noise. It's better. From a noise perspective, a resistor is better.
Voltage headroom.
Yeah, voltage headroom, right? So if I use this as a current source, as long as I have a few hundred millivolts across it, it's alive, right? If I use a physical resistor RO and run a current of, let's say my RO is 100K, and let's say I'm running 1 milliamp. Well, my uncle better be also in the voltage business, because I need 100 volts, right, across that resistor. So that's the benefit of a current source. It has low voltage headroom. The penalty is noise. Okay. And what's kind of cute here is you can take this expression for Rin and just rewrite it in terms of Vmin, right? Because Rin is proportional to 1 over Gm, and Gm is basically given by 2ID over V star, right? So if I just substitute here, you can see that Rin is proportional to Vmin, because here Vmin is also proportional to V star. So basically, the way to lower the noise of this current source is to operate at a large V star. But of course, that eats into your voltage headroom. So you have a trade-off here. If you want low noise, you're going to have to live with low voltage headroom. Okay? Questions or comments? And I think you guys all saw this in the homework as well, because essentially you're solving the same problem for the PMOS current source. Alright, well, you might think, I'll just go to another technology, right? Forget MOS devices. Let's look at a bipolar current mirror, okay? Or this could be a silicon germanium device. Can I actually get a silicon germanium device that's going to give me lower noise? And you do the calculation. Now, typically, when you design a bipolar current mirror, you use resistors. Why do I use resistors here?
Because the VBE changes are exponential, so you don't want huge changes in VBE mismatches, so you want to stabilize that.
Exactly. It's partly for mismatch, right? So if you basically, if you do a mismatch analysis of this could be a good homework problem, you can show that the mismatch of VBE kind of goes away and it becomes more or less an RE mismatch. So if you have good resistor matching, you get good current matching. But also, more importantly, it rejects the noise. So if you look at this expression, remember we just did this calculation. We found that the noise of this transistor is rejected by 1 plus GM-RE. Right? So there's that expression that we just calculated for the cascode, where RE now is a physical resistor instead of being a transistor. So this resistor is rejecting the thermal noise of this device. That's great, but it's also injecting its own noise, right? So this is the total noise. Okay? So here's a couple of examples. Let's say example 1, I don't use RE. Then the voltage noise is given by, or the equivalent noise resistance is given by 2 over Gm, which is basically, again, very small, right? Because a Gm of a bipolar transistor is small. So that means that without RE, it's a very noisy current source. In fact, it's worse than a MOS device. How about if I now use a very large value of RE? In the limit, what happens? In the limit, you just get the noise of this resistance. Well, that's good, right? I make that resistance really big, and then I don't get much noise, right? But what's the penalty again? Headroom, right? Because there's a huge voltage drop across that resistance. So in some ways, I can really relate this expression to the basically headroom, right? I can say that RE is basically constrained by the minimum voltage that I'm able to tolerate. So I can write RE as V min minus VCE sat, right? So let me just, it's always hard to use slides when it's, just draw here. So this is my RE, and the minimum voltage that I can get is I out RE plus a VCE sat. Okay, so I can write that RE is basically V min minus VCE sat over I out, and I'm going to multiply and divide by V min, and why do I do this? Okay, if I look at the Rn for MOS device, we have an expression that looks like this. So it's in order to compare it to the MOS expression. Okay. So in the limit, as RE goes to basically as GMRE goes to infinity, then the Rn of the BJT is given roughly by just RE, which looks like this, and you can see that it has a factor of V min over I naught, just like a MOS device, multiplied by another factor, which you can compare here. And you know, basically, if let's say V min is on the order of a volt, and this is on the order of a couple hundred millivolts, so this term is on the order of unity. If I look at this here, let's say gamma is on the order of 1, just to make things simple, and let's say k is 1, so this is also 1/2, let's say on the order of unity. So the first order, the Rn of a MOS device is the same that you'd get in a bipolar device that's been heavily degenerated. Okay? So to first order, there is no benefit in using a bipolar device. You're not getting any win, because really you're degenerating the gain away by using this large resistor in the first place to minimize the noise. Okay? Is that argument clear to everybody? Questions? Good. All right, so at the end of the day, the lesson to be learned is that current sources have basically a noise penalty, and that noise penalty is directly proportional to the, inversely proportional to the headroom penalty. So you have to really think carefully about how much headroom you're willing to give up in order to minimize the noise of a current source. And the same argument applies regardless of technology. Bipolars and MOSFETs have the same trade-off. All right. Well, cascode amplifiers are very nice. So are cascode current mirrors. The idea of a cascode current mirror, of course, is use that degeneration to get even higher impedance. So first of all, before we talk about cascodes, what can I do to increase the R out of a current mirror? Obviously, cascode is one way to do it, but what are some other techniques to use? Okay, degenerate it. In bipolar, that's a good choice. In MOS devices, there's almost no point to degenerating, because I can achieve the same effect by doing what? Just use a longer channel length device, right? I know the output impedance of this device goes up with channel length, so I can basically reduce the value of, I can increase R out by playing around with the W of and L of this device, and certainly I want to use the largest L I can get away with because that's going to give me the highest output impedance. Okay? So for instance, if you're in a 90 nanometer technology node, don't design your current sources with 90 nanometer. Design them with basically 1 micron or half a micron. And the way you know what to use is you'd go generate some plots, and you'd find out that, let's say, beyond half a micron, the benefit you get in RO with channel link scaling kind of stops, saturates. So half a micron may be the optimal point. In 0.18, you guys can run some simulations and find out what's probably the best point to use. But otherwise, if I use the longest channel length, I can always reduce the output impedance by playing around with the W of this device. Okay? Good. So what we're going to do is cascode the device, and actually, I guess to be fair, cascoding really is degenerating, right? So you were right. And it's actually kind of useful to review why cascoding, or why this degeneration has such a benefit, right? So we know that the output resistance of this guy is RO, and we probably all remember that the output resistance increases by 1 plus GMRO, where this is the loop gain. So the output resistance increases by the loop gain because of the series feedback on the output. Let me just remind myself how that happens, because it's going to give us, let me come back to that point, actually. I'll come back. All right. What's a disadvantage of the cascode, right? First of all, it looks like we have a huge benefit, right? GMRO is 20, 30, so I get a huge increase in output resistance. What's the price to be paid?
Headroom? Yeah.
Swing, again. It's always about swing. So definitely the lowest, the Vmin of this device is going to be higher because this gate device is biased at 2 VGSs, right? And the lowest I can bring this voltage, roughly, if I look at this voltage here, so VGS, if these are equal size, VGS is equal to VT plus V overdrive, right? So this is 2 VGS plus 2 V overdrive. So what's this point? This point is 2 VT plus V overdrive, right? This is actually VT plus V overdrive if I subtract out a VGS here. So this point is held at 1 VGS, which is VT plus V overdrive, and that means that the best I can do is VT plus 2 V overdrive, right? Because if I go below this voltage, this device will go into triode region and the output resistance drops. Okay? So compared to a normal device where I could go down to an overdrive, I have a huge penalty of 1 overdrive plus a threshold voltage. Maybe we can solve this problem, actually. Let me show you some simulation results, just for good measure. This is basically a simple cascode, and the way I'm going to solve this headroom problem, partially, is by realizing that there's no reason why I have to bias this point at 2 VGS plus 2 VT. Right? I could always lower this voltage to the point where I just come to the threshold of keeping this device in triode region, or in saturation, right between the boundary. So in fact, in order to do that, I really shouldn't bias this more than, let's say, 1 overdrive plus 1 VT, 2 overdrive plus 1 VT, not 2 VT, right? But we'll do that calculation more carefully in a moment. But for the moment, for this simulation, it's just at a fixed value. And then here's a comparison with a regular transistor, and here's in the results. So as a function of V out, you can see that this is the regular device, and it has about 10 mega ohms output resistance. And the range, right, let's say that you were targeting 1 mega ohm, you might be able to go down to, down to, let's say, 500-600 millivolts, all the way up to close to 3 volts. Now, if I put in a cascode, something very interesting happens. First of all, the of course, we get that huge boost, right? 1 plus GM times RO boost in the peak value. And as far as the swing goes, you know, if now you're shooting for a higher output resistance, let's say you're targeting a gigaohm, you can see that you have a much smaller swing compared to here where we're just going for a megaohm. That's not really a fair comparison because now we're getting a gigaohm. But still, the drop happens because one device is going into triode and then the second device goes into triode. So in this region where both devices are in triode, you can see the output impedance is roughly the same. Now, the other issue is how do we actually bias the drain source voltage of the first device? Okay, so here is the observation. If I can just choose, if I could magically program a voltage into here, what I'd like to do is program a voltage which is some fraction or some multiple of the V star of this device. I'll just call this V overdrive because it's more intuitive. For a long channel device, I know I would program this voltage to be exactly overdrive, right? So this voltage here would be 2 VT, 1 VT plus 2 overdrive to keep this voltage here at overdrive. But because this is a short channel device, concept of overdrive is a little bit, you know, yeah. So maybe I need to have a little margin here. So I might make K 1.5. Or maybe I can be more aggressive and make K 0.7 or 0.8. What I'm going to do is I'm going to use a simulator to determine how large I need to make K. So here's a simulation where I've chosen different values of K, starting out with basically the baseline simulation. This is the single device, and then as I introduce increasing values of K, I get higher and higher output impedance. And so here you can see that making K larger than 1 is actually nice. I get even more output resistance. So clearly this boundary between triode and saturation region was not as simple as I thought. I had to use a higher value of K. Okay, so what the problem now is that we know that we can solve the headroom problem, at least to some degree, by biasing up the gate of our cascode device through a custom voltage. That custom voltage needs to have basically overdrive voltages in it and VTs in it. Okay, so why not just plug in a constant voltage there, right? Figure out with SPICE what the overdrive voltage is, what VT is, and just plug in K times VT plus 2 overdrive. Why not do that? Yes?
Once you manufacture it, process variations will change VT and you'll have a useless voltage.
Exactly, right. So we want this voltage to track. We want this voltage to track process and temperature. So we want to automatically generate this voltage, right? And so there's lots of circuits for doing that. And let me just talk about one of the simplest circuits, the simplest to understand, which is not in your slides, but you'll find it in Gray and Meyer. So the simplest way to do this is just come back and observe that on the reference path I have 1 VGS plus 2 VGS. Let's call this M1, M2, M3, M4. So this voltage here is 2 times the overdrive voltage of these guys plus 2 VT. Over here, what I'd like is this transistor to have roughly an overdrive voltage on it. And so an overdrive plus a VGS, right? VGS is VT plus an overdrive, means at this point should be VT plus 2 overdrive. So what I'd really like to do is to insert a battery here that generates a voltage VT and just subtract the VT out. And if this VT tracks process and temperature, then the circuit will work. Right? clear to everybody? Now this circuit has a name. It's called a high swing cascode because it allows us to really maximize the swing that we can get out of this cascode by operating this transistor at the threshold of triode region. Okay. Incidentally, what's the lowest voltage I can go? Well, the lowest voltage I can go is when this device is at the edge of saturation. So let's do that calculation a little bit carefully. So V min is basically a V overdrive plus VDS2 min, right? And so VDS2 min is equal to VGS2 minus VT, right? And what's VGS2? It's also V overdrive plus a VT minus a VT. So V min is approximately 2 times the overdrive voltage. Okay? So let's now, so here's one way to synthesize this circuit automatically. So here, I'm going to bias up my cascode device like this. And again, so this is my reference path. It's diode connected. This is my output. And so again, I want this voltage here to be overdrive. This voltage here to be 2 overdrive plus a VT. If I add another VGS here, if these W and L over L's are the same for all the circuits, then I get 3 overdrive plus 2 VT. Okay? And this point, of course, is also at V overdrive plus VT. So what I'd like to do is have a device, let's call this M3. What I'd like is that VGS of 3 to be equal to 3 overdrive plus 2 VT minus V overdrive plus VT, or 2 V overdrive plus VT. How do I make a transistor with twice the overdrive voltage of, let's say, all the other transistors?
Make the W by L 1/4.
Right. I just make this 1/4, and the overdrive voltage is twice. All the other transistors are unity, right? So this is M. And basically this circuit will give me exactly what I want. Questions or comments? Yes.
You wanted the VT drop. Why didn't you use a W over L that's so large the VGS would be about VT? So
That's another way to do it. Yeah, you could do it that way as well. Now, what are some issues with this circuit? It's staring you right at the face. There's a problem with this circuit. Let me give you guys a hint. There's a systematic error in this current source. What's the source of that systematic error? Anybody? Yes, Timothy. What you mean in the way I've drawn it? Yeah, but that's okay because the current is also set by this mirror, right? So the current of this path is fixed by this guy. So basically I want the same current to flow in all branches in the way I've drawn it. And so the current for this path is determined by, the current in each path is determined by this current mirror here. So that's okay. That's fine. What's the systematic error? Yes. Perfect. Yeah. This is my reference path, right? So the VDS here is V overdrive plus VT. This is my output device. It has a VDS of V overdrive. So there's a built-in systematic error in the circuit, and that's not good. And that's actually pretty easy to fix. What's another systematic error in this circuit? Anybody? Well, I've been throwing around a lot of threshold voltages, right? And we all know the threshold voltage varies with body bias, right? And so these transistors, because they're NMOSs, unless it's a triple well process, the VT is going to vary. And so there's going to be basically VT mismatches because the sources are all at different potentials. And so this is also going to be sensitive to body effect. Okay. Let's look at some of these slides. So these are some different solutions. There's actually a lot of different high swing bias circuits, and they all have more or less the same flavor. So if we analyze a couple of them, I think you'll get the idea. So here's a device which is nice because it's actually quite simple. So the idea is that here's my regular device, M1, and I'm going to bias this up with a current mirror here, biased through IREF. Okay? And for the moment, let's forget about this transistor. Let's just ignore it. And to get my VGS value for the VG value for M2, all I'm going to do is scale a device, run some current through it, and because this is a scaled device, I'm going to get roughly the right VT plus overdrive voltage here. So for instance, if I want 1 VT plus 2 overdrive, I just make this a quarter size device. That's the same trick we just played. So this device biases up this transistor okay, and this transistor here is our reference path. So let me just redraw this simplified version of the circuit. So this is 1/4 size. That generates the right bias for my cascode. And then for my mirror, I do that. Again, it has all the, this is even simpler, right? You might say, why'd you bother with all those transistors? This is it. Well, I can make this structure even better because I can get rid of the systematic error we just talked about with the VDS. So the VDS of M1 is V overdrive, whereas the VDS of this guy is V overdrive plus VT. All right? So the way to get rid of that systematic error is basically use a circuit like this. So replace this transistor here with this transistor, where this voltage is also biased to this point, and so this voltage minus a VGS produces the same V overdrive voltage on this transistor, which is in my reference path. Okay, so now I'm going to get rid of this guy and connect this point, excuse me, to here. All right, that's pretty messy, so let's look at the slide. All right, so here's the slide. Again, there's that quarter device. I take one VGS down, and that produces a V overdrive on this transistor, which then mirrors its current to the output. Both M1 and M3 are biased at the same VDS value, so that gets rid of that systematic error. Unfortunately, I still have an issue with the VT mismatches due to body effect, right? The other thing you may be worried about is this transistor configuration. What's the VDS of M5? Let's draw it. Let's just calculate this real quick, because this is a nice little building block that we'll use again and again. So what I've done is I've taken the gate voltage and presented it to the drain, and this is biased at 2V overdrive plus a VT. And this point is just a VT plus a V overdrive. And this point here is just V overdrive, right? So this transistor M5, VGS of 5, is equal to 2V overdrive plus VT minus V overdrive, which gives us a VT plus a V overdrive. So VGS 5 minus VT is an overdrive voltage. Okay. What's VDS of 5? VDS of 5 is VT plus V overdrive. This is this voltage, which is connected here, minus V overdrive, which is the source. So that's equal to VT. So this transistor M5 will remain in saturation as long as, again using square law theory, as long as VT is larger than V overdrive. Okay? So we have to be careful to make sure that this is actually satisfied for our technology. But, you know, if we're putting this at 100 millivolt overdrive and our VT is 300 millivolts, then clearly that's a safe bet. All right? Questions or comments? Okay, here's some some plots of that high swing cascode, and you can see that this is the output resistance versus the different process corner. This is the 0.35 micron technology that was used in the previous semesters. What's the difference between these plots? So this is as a function of K, so obviously you want to use a large value of K here. And then this is as a function of just process. So you can see on the low side, the process variation is actually pretty minor. This is kind of the triode region where they all more or less look the same. And even here, the process variation is, let's say, 30% or so for this device. Okay, here's another version of that high swing circuit, which is exactly the same, except instead of using one transistor here, I use a bunch of transistors. Why would I do that? Right? Instead of using one transistor with W over L of 1/4 or 1/5 or whatever you like to get just the right K times V overdrive, I use a bunch of series transistors. Am I crazy? Why would I do this?
Better matching?
Okay.
You're using the same device over and over again?
That's part of it, but there's a better reason to do this. Yes?
Some of that body effect can be compensated.
That's right. So the trick is that because the voltage from here is gradually increasing up to the full, let's say, 2 overdrive plus VT, these transistors are experiencing body effect. And so to some degree that matches the body effect experienced by this transistor. And so this is less sensitive to body effect. I mean, it's not perfect, but it's a solution. Okay? Questions or comments about that? Yes.
So in all these designs, so if we go to the short channel regime, and so the sizes that we have all derived 1/4 exactly, none of these will be exact. So how do we go about designing these things? Because we have to decide what's the overdrive voltage will be, how the VT will change with channel length, and
that's why you make good money as an analog circuit designer. It's not that simple. You can't just take the textbook solution and use it. But you know, I mean, the nice things about these circuits are, first of all, you're using long channel transistors because there's a good reason to do it, to get the high output impedance. That means that square law is pretty much valid here. You're not too far off using square law theory. And what you're really doing is, you don't need a precise voltage, right? It doesn't need to be exactly VT plus 2V overdrive. In fact, you'd be dumb to do that. Or you're going to have some margin. So all you want is that margin over temperature and process shouldn't drive transistor M1 into triode region. And because you're deriving your overdrive voltages from like transistors, they're going to track very well with process and temperature. So you're designing a circuit that has inherently good process temperature variability because you have this built-in margin. You don't need to hit that voltage within a few millivolts, right? You're going to hit it within tens of millivolts, maybe even hundreds of millivolts. Okay, we'll stop there.